This video is on quantum numbers. These are in your book on pages 107 to 110. It'd be a really good idea to read those pages in addition to going through this video. Make sure you're taking good notes and listening to everything that's being said along with what's being written down. And make sure you pause and rewind as needed. So, quantum numbers are related to where electrons are in an atom. Each electron in an atom is described by 4 quantum numbers. The Pauli exclusion principle states that no 2 electrons in an atom can have the same set of 4 quantum numbers. I like to look at this as an address. Okay, these 4 quantum numbers start out with the most broad, like if we were talking about your address, it'd be maybe like the state, and then they get more specific. So then the next one is going to be more specific as to where it is. So that'd be like in your city, and then getting more specific would be your street, and then even more specific would be which house or apartment or building on that street. So these electrons, they live in orbitals that are in sublevels that are in energy levels. So these are kind of our address. So energy levels are going to be our most broad, and then within that energy level you have a sublevel, and then within the sublevel you have an orbital. There are 2 electrons that can fit in each orbital. So Pauli exclusion principle says that no 2 have the same set of 4 quantum numbers, which means no 2 electrons have the same exact address. They're not in the same place at the same time. So if there can be 2 in each orbit, what that means is they're actually in different spots within that orbital. So that's what we're going to go through. So the first, and an orbital describes where you can find an electron 90% of the time. We talked about that Heisenberg's uncertainty principle. So we're talking about this 90% of the time. This is where it is. The other 10%, we don't really know exactly where it is. It's somewhere else in the electron cloud. So first quantum number is the principal quantum number, and we use a lowercase n to represent this. So this is the most broad. The number n, this principal quantum number, it can be 1, 2, 3, 4, 5, 6, 7, whatever. It's going to be a positive integer starting with 1. And this defines the energy level of the electron. So these are like those rings from 9th grade science. These are what we call the energy level. Sometimes we call them also the orbits. So this would be, if this is your nucleus, these would be these rings. Okay, so the first one would be n equals 1. The second one will be n equals 2, and so on. There we go. The larger the number, the larger the size of the orbital, and the farther away from the nucleus. Just like 2 is a bigger number than 1, it's further away from the nucleus, and it's also a bigger energy level. The maximum number of electrons in the energy level is determined by a formula, 2 times n squared. So the bigger the energy level, the more electrons it can hold, the more space it has. So each energy level has a maximum number of electrons. And you might remember this from 9th grade. So if n equals 1, you can plug 1 into that formula. So 2 times 1 squared. And remember, you have to do the exponent first. So 1 squared is 1 times 2 is 2. So 2 electrons total can fit in that first energy level. That's it. The second energy level is bigger. So when you plug it into the formula, you get 2 squared is 4 times 2 is 8 electrons. So for n equals 3, 4, and 5, why don't you pause the video right now and figure out how many electrons can fit in each one. Okay, so for n equals 3, you'd have 2 times 3 squared. So that would be 3 squared would be 9 times 2 is 18 electrons. For 4, you'd have 2 times 4 squared. So 4 squared is 16 times 2 is 32 electrons. And for 5, 2 times 5 squared. So 5 times 2 is 25 times 2 is 50. Okay, and we could keep going, but we'll stop there for now. So the next quantum number is called the angular momentum quantum number. So this is represented by an L, and it's usually written in cursive like this, so you can tell it's an L and not a 1. So L can be 0, 1, 2, and it's going to actually be a whole bunch of numbers. So 0, 1, 2, and it's going to go up to n minus 1. So hold on, this will make more sense in a second, but these are the sublevels that I was talking about. So within the energy level, these are these sublevels. So here's a little chart. If n equals 1, so L can go up to n minus 1. So n minus 1 would be 0 then. So L would just be 0. It's going to go from 0 up to n minus 1. So if n equals 2, L is going to be 0 or 1. If n equals 3, L is going to be 0, 1, or 2. The number it stops at is going to be n minus 1. So they determine the orbital shape of that in the sublevel. So each sublevel has a different shape. Okay. So an orbital is a space that can be occupied by 0, 1, or 2 electrons with the same energy level, energy sublevel, and spatial orientation. So the sublevel I was talking about, oh, sorry, this is in the way. So if L is 0, so like n equals 1, L is 0, you have what we call an S sublevel. If L is 1, you have a P sublevel. If L is 2, you have a D, and if L is 3, you have an F sublevel. So these are the different sublevels, and I'll get to them in more detail in a second. But what that means is, if n equals 1 and L equals 0, that means in the first energy level, that's the n equals 1, you have an S sublevel. In the second energy level, you have L being 0 and 1, which means you can have an S and a P in the second sublevel. Why do you get more in the second, energy level? Because it's bigger. In the third energy level, L is going to be 0, 1, or 2, which means you're going to have an S, a P, and a D sublevel. Okay? And in the fourth energy level, oops, should be a comma 3 here, add that in there. You should have S, P, D, and F. All of these are possible in this fourth energy level. Okay? So what are these sublevels? Oh, maybe I'm not quite there yet. Oh, we'll come back to them in a second. So the third is the quantum number is the magnetic quantum number, and we use a lowercase m to describe this. And m is going to be a range from negative L all the way up to positive L. So going up through 0. Okay, so really the actual number doesn't mean anything to us. What matters is how many m values they are. The number of m values tells you how many orbitals there are. So you could think of this as like a house, let's say. Okay, so maybe the energy level is your house, or your street, I suppose. The energy level is your street, and there can be multiple houses on the street. So the S is a small house, the P is a bigger house, the D is a even bigger house, and the F is the biggest house. M is going to tell you how many rooms there are in that house. Okay. So each orbital is a different orientation in space. What that means is it might be set up so that it's like on like the x-axis. It might be set up so it's on the y-axis. So different orientation, or the z-axis. For example, if n equals 2, this is from that last table, L is going to be 0 or 1. Remember, because L goes up to n minus 1. So if we just deal with L being 0, then M is going to be 0. Remember, because M goes from negative L to positive L. Okay, so that would be 0 means it's an s orbital. There's only one m value. It means it has one orientation. Okay, now let's say L is 1. If L is 1, now we have a p orbital. Okay, so m is going to be negative 1, 0, and positive 1. There are 3 m values, which means a p orbital has 3 orientations in space. Okay, so let's talk about these different sublevels and their orientations. So first we've got an S sublevel. S sublevel is spherical in shape. It contains one orbital, because this would be L equals 0, so M equals 0, so you have one orientation, so you get one orbital. So it can fit 2 electrons. 2 electrons fit in each orbital, and you can see I drew in little red dots for my electrons in here. That's the maximum. Can it hold less? Yes. Okay, and you can find an S sublevel in every energy level. So you can find an S in the first energy level, the second, the third, the fourth, and so on. So the next one is a P. So this would be L equals 1. And if L equals 1, M equals negative 1, 0, and positive 1. So P is what we call a dumbbell shape. Okay, you can see the pictures here. The bottom picture is when you put them all together. And because it had those 3 m values, it has 3 different orbitals. So they have 3 different orientations in space. So you could have one where it's on the x-axis. You can have one where it's on the y-axis. So you see it's differently set up in space. And then you have one on the z-axis. So the bottom is when you put them all together. So bottom is a p orbital. It's got all 3 orientations. 2 electrons fit in each, so a p sublevel can hold 6 electrons total. So it's kind of like a P, if you have this house, Okay, and you call it P. It has 3 rooms in it, and 2 electrons can fit in each room for a total of 6. Okay, P sublevels are big enough that they don't fit in that first energy level. They start in the second, so second, third, fourth, and so on. Next is the D sublevel. And a D sublevel is shaped like a clover leaf you can see in those first 4 pictures. And then there's that 5th one is where it's the dumbbell shaped like a p orbital and it's got a little donut around the middle. There are 5 different orbitals here. So D is when L equals 2. So M equals -2, -1, 0, +1, +2. So there are 5 different M's. So there are 5 different orbitals and different orientations. You don't really need to know the orientations. Just know that there are 5. So we got 10 electrons total, 2 in each. 5 total, 5 rooms, 2 electrons fit in each. So 5 times 2 is 10. And D is big enough that it only starts in the 3rd energy level. Can't fit in the 1st or 2nd. The last sublevel is an F sublevel, and this is the biggest, and it's the most complex, and that's why you don't see any pictures. I've never seen a picture of what they think an F sublevel looks like. What you need to know is that it has 7 orbitals. So because L equals 3, so you've got for M, -3, -2, -1, 0, +1, +3. So you've got 7 different orientations, so 7 orbitals, 2 electrons fit in each for 14 electrons total. And F is big enough that it will start in the 4th energy level. It doesn't fit in 1st, 2nd, or 3rd. All right, so our last quantum number is what we call the spin quantum number. So this relates to the 2 electrons in the same orbital. So the S can be +1/2 or -1/2. All this means is that when they're in the orbital, one spins one way and the other spins the other way. Okay, so it describes the orientation or spin. Because remember, Pauli exclusion principle says no 2 electrons can have the same 4 quantum numbers. So they could be in the same energy level. So they could be in the 1st energy level. They could be in the same sublevel. So they could both be in an S. They could be in the same orientation. But then they have to be have different quantum numbers. So one spins clockwise and one spins counterclockwise. That's their difference. Okay. And just a quick summary chart. So it kind of goes through if N is 1, 2, 3, or 4, the possible L's, the possible M's. Sublevel, remember, relates to L. Okay, so L tells you sublevels. Okay, number of orbitals relates to how many M values they are. Okay, and remember the maximum electrons is going to be your orbital number times 2 because we get 2 electrons in each orbital. Okay, so that's the lesson on quantum numbers.